Today we're going to look at some applications of polynomial functions. We'll do one example. Mr. Miller has another example in his notes as well, so go have a hunt around and see if you can get further information should you require it. We've got a rectangular box with an open top is to be constructed from a rectangular sheet of cardboard. Okay, so as usual, like raw material comes in like this form here. And what manufacturers do is take that raw material and convert it into something that they will either put a product in or I don't know what they're going to do with it. Anyway, that rectangular sheet of cardboard is 20 by 12. And what they're going to do is just chop squares out of the corners like so and fold the four corners or fold the remaining kind of flaps up, I suppose, to form a box. Okay, so the box has length L, width W, volume V, centimeters cubed. I want us to draw the rectangular sheet of cardboard. That's kind of just what we did. Let's just do it more formally. So 20, 12, with a chunk or a square cut out of each corner, of which the square is side length X. And the rectangular sheet of cardboard, that now we need to draw the 3D sketch of the box. You don't need to be some brilliant graphic designer, believe me. I can talk to you about my graphics results in high school if you really want to talk about that stuff. Now this is the length, this is the width, and this is the height. Okay, so there we go, we've got everything we need. Express L and W in terms of X, and hence express V in terms of X. So if we're trying to find the volume, it's going to be length times width times height, okay? And at the moment, the only thing we know is the height is X, okay, because that's the fold or the square dimensions is X. So our volume formula at the moment is L times W times X. And what we want to do is get L and W in terms of X. And you might note that what will happen then is we get volume in terms of one variable only. And that's the same thing that we've been doing for quadratic functions as well. Okay, how are we going to do it? Well, this is the length here, 20. And when I fold it up, the actual length is going to be 20 take away whatever this value of X is here, this and this. So that's going to be the actual length of the box. So 20 take 2x. I'm going to say L is 20 take 2x, and width is going to be similar, 12 take 2x. And what I'm going to do is write my volume function now. V equals 20 take 2x, that's the length. Width is 12 take 2x, and the height is x. Now I've just noted here, often this question will be a show that this is the function, okay? So we'll continue along and show that it is, even though it doesn't or it's not a show that, I'm just going to presume it is. So 12 multiplied by 20, 12 twos are 24, that's 240, take away 24x, take away 40x. I forgot to add 4x squared, all multiplied by x. Then we're going to expand that. 4x cubed, take away 64x squared, take 240x as required. Select an appropriate domain for V, that is, the restrictions on the values x can take. Well, to be honest, I wouldn't have a clue, okay? And I never have a clue until I see the graph. So let's go to part D and actually sketch the graph first. So we've got V against X, and we're going to use this form of V to sketch the x-intercepts. So we're going to go 0 equals 20 take 2x, 12 take 2x, x. And it's going to have intercepts at 0. This one's going to be 6, and this one's going to be 10. It's a positive cubic, we can see there. So positive cubic, start positive, and that's our function. Now, we're not done yet though. Okay, so we're going to sketch the graph of V against X for appropriate values of X. Now, the only appropriate values of V are ones where it's more than 0, i.e. we produce a volume. So the first thing I'm going to do is start to remove parts of this graph. Now I'm going to get rid of this part because that produces a negative volume and it also uses a negative value for X. So it's a double whammy on that one. Now this part here also produces a negative volume. So we're not interested in negative volumes. All right, so we're going to get rid of that part. All right, so here is where we produce a positive volume between 0 and 6 and 10 onwards. Okay, but it's this part here that produces, or that we're going to talk about a little bit more. Okay, so note that this part here, we've got values of X greater than 10. Okay, now if you have a think about how that might happen or why it's gone positive again, what happens is think about values of X greater than 10, i.e. let's go 20. If I sub 20 into this length function here, you notice that this is going to be negative. If I sub 20 into this function here, you'll notice that this is going to be negative. And the reason it comes out positive is that a negative times a negative times, in this case, the X value of greater than 10 of 20 is a positive number, will end up being a positive value or a positive volume, okay? So that is what's going to happen there. So to get these values here, you need a negative length and a negative width, okay? Now we know that that's not going to make a box. You can't make a box of negative length and negative width. So actually, even though the graph says I can produce a positive volume for values greater than 10, we're going to say that in the applied situation, in the scenario that we're in, it's not going to make sense in context. So I'm actually going to get rid of this part of the function as well. Now that leaves us just with the 0 to 6. And because we want V to be greater than 0, I'm going to put some open circles at 0 and 6 to indicate that a 0 volume is not acceptable. Okay? And now we can actually state the restrictions. We're going to say that X is an element between 0 and 6. Those numbers there are the only values of X that are going to produce a legitimate volume. All right, now what we want to do is calculate the length and width and height that maximizes the volume of the box. That's going to be the maximum volume. Now, it does not happen at 3. Okay, so the midpoint of a cubic function is not the maximum. Okay, so again, be very careful with cubic functions. They behave differently to quadratic functions. So to get this maximum here, the reality is what we're going to have to do is go to our calculator. So we're going to go to Menu, Graph, and Table. And what I'm going to do is just clean out this stuff here and return to the default Cartesian plane scale. Okay, now let's type in our function, which we can type in the factorized version or the full version, doesn't really matter, the expanded version. Let's graph it. Okay, so you can see here pretty quickly that we got that certainly correct, 0 to 6. So we got the maximum, which is somewhere up here. So what I'm going to do is change these dimensions and change the max. Now it looks like I'm not even close, so I'm going to guess 100 and see if I hit it. And I'm still not very close, so I'm going to try 300. All right, we got it. So there's our maximum value. So what I would do is go analysis gsolve and use the max command. Okay, so here's method 1, which is graph and gsolve. And what we're going to do is note that it's 2.4274 and the max volume is 262.68226 ... Okay, so that's an approximation. All right, and that's going to be acceptable in this case because it says round your answer to 2 decimal places. Okay, now what if it didn't say round your answer? What would we do then? Well, here's method 2. And this is more likely to be the case of what you're going to do next year in 3-4 methods is get the exact value. So here's the method I'm going to use. What I'm going to do is take a copy of the function, edit and copy, and go into my main screen. Now we're going to use interactive calculation and we want fmax. Okay, that's function max. All right, so you put your function in there where it says expression. The variable is x in this case, and you tell it where to go hunting for the maximum, which in this case is between 0 to 6. Gave us the same thing, but watch this. If I go into standard mode and re-ask the question, it actually gives me the exact value. So the method here is fmax through interactive. And that tells us that the maximum value, or the x value that produces the maximum, is -2 root 19 on 3 plus 16 on 3. And the maximum value is 262, or exactly 16 root 19 over 27 plus 1792 on 27. So not a pretty number. I never said it was pretty, but that's the exact answer. But this question did let us round it, so we can use this method to acquire it. Okay, so calculate the length and width and height that maximizes the volume of the box. So what I generally do is I write out each of the dimensions, length, width, and height. All right, to 2 decimal places. So we already know the height is 2.42. Is that a 2 or a 7? I'm not sure. .43 to 2 decimal places. So again, very important that you put the unit in here. Now the width, what we're going to do to get the width is to substitute it into our definition for width, which was this one here. So we're going to go and say 12, take away 2 lots of, and we're using this value for x. We're going to try and use the most exact version of it. So grab all the decimal places to quote the width in this case as 7.15 centimeters. Now the length was similar. I think it was 20 from memory. Yeah, 20 take 2x. Okay, and so that one is 15.15 centimeters. Now what should happen is if I multiply all 3 of those together, 15.15 multiplied by 7.15 multiplied by 2.43, what should happen is it should produce this maximum volume of 262.68 because they're the dimensions that give us the largest volume inside the box, 263.22. Now have a think about why that may have happened. Why didn't we get this exact volume? And if your answer is because we rounded these numbers, absolutely correct. Okay, so we've rounded the numbers, which means that we've affected the precision of the overall result, but that's okay because we were told to do it. Okay, pretty tough problem here. We've got a piece of wire 50 centimeters long. There it is. It's cut into 2 pieces. So, I don't know, there maybe. Not into 2 equal parts, note. Okay, one piece, so if I imagine I slice it there, this piece we'll say we're going to make a square out of. The other, we're going to do a circle. Okay. Now, what we will do from here is find, what we're attempting to do is find the smallest possible sum of the area of the square and circle in centimeters squared. Okay, so we need to make an area function that is the addition of the area of the square and the area of the circle. All right, well, what do we know? We know that the length from here to here is 50. Okay, so that length there is 50. And what we know is the square is going to be cut, and that's going to be x long. We're going to say that that's x long, which means that the length of this circle is going to be 50 take x. Okay, so that's how long around the circle, that's how long around the square. All right, so let's imagine what this would look like then. So here's our square, and its perimeter has got to equal x, which is going to make each of its side lengths those, x on 4. Okay, so x on 4 plus x on 4 plus x on 4 plus x on 4 will equal x. Now over to the circle, and you've got to go back to year 8 or year 9 whenever you learnt the circumference of a circle to work out this one, because that length there is actually going to be our circumference. So our formula is circumference equals 2 pi r or pi d. All right, so what we're going to say is that circumference, which in this case is 50 take away x, is equal to 2 pi r. Now, what do I do from here? Well, I need to make an area function, okay? And the area of this square is easy. Area equals x on 4 times x on 4, length by width, which is going to be x squared on 16. All right. Now this one here, the area of a circle, recall, is area equals pi r squared. Okay, so what I need to do is find r, or find this, or use this to find r in terms of x. Okay, now that's going to mean r is equal to 50 over x take away over 2 pi. So now that I've got r in this form here, what I'm going to do is sub it into that, and I'm going to say area equals pi multiplied by 50 take x, 50 take x all over 2 pi, and it's going to be squared. All right, so find the smallest possible sum of the area of the square and the circle in centimetres squared, correct to 2 decimal places. So what we're going to do is find the sum of the areas. So I'm going to say that overall area function, a of x, is equal to the area of the rectangle plus the area of the circle, which is pi 50 take x over 2 pi all squared. Okay, now it's important to note here that we've got it in terms of x. Some students have trouble with pi being there, going, oh, it's 2 variables, but remember, we know exactly what pi is. It's 1415,92654. It's a number just like any other number, 50, 16, pi is just a number. Okay, so what we're going to do is minimize this. Now, how are we going to minimize it? Well, we're going to do this problem on the calculator. So we're going to go to our graph screen, graph and table. And what we're going to do is type in that function. Now, be very careful with how you input it. So x squared over 16 plus shift pi multiplied by shift divide 50 take x over 2 shift 0, and we're going to chuck that all in some brackets and square it. All right, so there is our function. Now let's graph it. Where is it? Okay, so what we know is this length here, x, will start to increase. We're going to start to increase this x value, and what it's going to do is produce areas. Okay, now the area, if we think about it, it's got to be larger than 4. Okay, so what we're going to do is start to amp up these y values here. So let's see if we can find this function. So I'm going to change the maximum volume, or the y max, from 4. Let's see if we can find it at 100. We haven't found it yet. So we're going to hit it again and send it up to, I don't know, 300. Aha. All right, so we've found the function. So what happens at 0 is it gives us this value here, and the area starts to decrease. Okay. Now let's increase those x values now. So it's at 7.7. Let's chuck it up to 30. Okay, and we can see where it's starting to get to the lowest point, so I'm going to increase that even more. All right, and there's our minimum. Okay, so what we're going to do now is go analysis, GSolve, and we're going to go min. Okay, here it is. So we're going to say here that when x is equal to 28.005 ... a of x, the function or the area is 87.515 ... All right, now let's go back and then see what the question was asking. Find the smallest possible sum of the area of the square and circle in centimeters squared, correct to 2 decimal places. So there we go, we've got it now. So let's just finalize that by saying, therefore, 87.52 centimeters squared is our smallest area.